So, quick reminder, I don't actually have it up here, but Lab 4 is due tonight. Hopefully everyone's pretty much done with that at this point. And then Lab 5 is coming up for next week. It'll be due on Thursday of next week. So today we're going to continue learning about caches. So we're going to start off with just a very quick summary of where we left things last time. And so if you recall, last time we went through a whole slew of different types of memories that are available to us and what they looked like and when we might want to use each one. And so we ended up with this memory hierarchy where we essentially start off with registers being our fastest, then we have potentially multiple levels of cache which are implemented in SRAM. We have our DRAM main memory, then a flash drive, and then a hard disk. And the further down you go, the slower the performance, but the more capacity you can get. So today we're going to go into the detail of these hardware caches and how exactly one goes about using them. And as I mentioned last time, in a few lectures, we're going to get to virtual memory and how we do these kinds of things in software. And in either case, though, the main concept is the same, which is we want to pretend that we have a larger memory than we actually have and that it all runs as fast as possible. Okay, so quickly, to recap again from last time, we said that if we want to try to get something from the cache, suppose that my processor wants to get the address 0x6004, okay? There are two possible outcomes. Either it's in the cache or it's not. So if it's in the cache, then what I get is a cache hit. And so what this means is that I'm going to be able to get the data that I'm looking for very quickly, and the cache will send that data right back to the processor, and so I can make use of it. The second alternative is when I look for something that's not in the cache. So suppose this address 6034 actually causes a cache miss. Then what's going to happen is the cache is going to reach out to main memory. Main memory is going to send that data back to the cache. The cache is also going to store it now for future reference in case I ask for the same address again in the near future. And then we pass that data back to the processor. Okay? So with a single level cache, that's basically how things look. And in all of these different types of memories, you can kind of think of each one being a cache for the level below it. In terms of making it, appear like that, with the one that's more capacity is just as fast. Okay, and so we ended with this basic cache algorithm, which looks like this. We basically want to say, okay, I have my CPU on one side, my memory on the other, and then I have this smaller memory which is going to store some of my data in it. Okay, in order to know which pieces of data I actually have, I'm going to store a tag which is going to give me information about the address of the piece of data that's in the cache, in addition to the data itself. Okay, and so if I want to look up memory location X, if I have one of these tags is equal to X, then I get a hit. And in that case, all I do is I pass along the data that's on that line in the cache back to my processor. If I want to write to that location and I get a hit, then I'm actually going to write into that memory location in the cache. But recall that this actually is referencing an actual location in main memory. So in addition, I need to initiate a write to main memory in order to keep the cache and my main memory consistent. Okay? If the tag that I'm looking for is not in my cache, then we have, first thing we have to do is, assuming my cache is full, I need to decide which piece of data I'm going to take out of my cache. We are going to talk today about different kinds of replacement policies that one might use. And then if I do a read, I would basically get the data from main memory, bring it into my cache. I will now have it stored in my cache, so I want to set up the tag and the data accordingly. And then I give that back to the CPU. On a write, it's similar, except that in addition to trying to write to main memory, I also want to load the data into my cache so that if it gets requested again in the near future, I'll get a hit the next time. Okay? And so that's where we left things. And today what we're going to do is we're going to start looking into the details of what kind of caches do I have, how do we build them, and how do we go about searching to see whether or not the cache contains the data that we're looking for. So we're going to start off with what's called direct mapped caches. The way that direct map caches work is that given a particular address, which is the address of your data in memory, it can be mapped to exactly one line in your cache. And the way that you figure out which line in your cache it maps to is as follows. The bottom 2 bits here we call the offset bits. So these 2 bits are basically always 0, 0 because recall that our addresses are in bytes, but we want to access an entire word at one time. Okay? So this is going to get us to our word boundary. The next set of bits are what we call our index bits. So if I have a cache that has 8 locations, I need 3 bits in order to address that cache. And so I'm going to use the next 3 bits of my address to pick one of the lines in my cache. Okay? And so what this means is that if I have this address here, the way that I'm going to see whether or not it's present in my cache is I will figure out what the index for this particular location is. It happens to be 2. And then I will look up that line, and then what I do is I look at the data that's in that line of the cache. So I have one piece that's the actual data, one piece that's this tag, which is storing information about my address, and I have a 3rd bit here, which is a valid bit. Who has any idea of what I might use this valid bit for? Any guesses? Well, basically, when we start up, our cache is invalid, okay? But even though it's invalid, you have some kind of binary data in there, okay? So we want to be able to have a way of identifying whether the data that I'm looking up is actual real data or garbage. And so essentially, once I bring something into my cache, I set the valid bit to 1. And so now if my valid bit is 1, then I know that it's actual real data that came from my main memory. So what would happen is I would look at the remainder of my address, compare that to this tag field over here, and then I would check, is my valid bit set to 1? And if so, I got a hit. Otherwise, I got a miss. Okay? Pretty clear so far, I hope. Any questions? Good. Okay, so let's take a look at an example. Suppose that I have a cache that has 64 lines in it. It's a direct map cache. And because it has 64 lines in it, I need 6 bits in order to identify which line I'm trying to access. Now suppose that I want to read memory locations 0x, 4000, and C. First thing I'm going to do is I'm going to convert this into binary. Okay? And so now, once it's in binary, I can divide it up into the different portions. So we've got here the bottom 2, which is the offset. The next 6 bits are going to be the index into my tag, and the rest of it is going to be, the index into my cache, and the rest of it is going to be what I compare to the tag. Now, why is it that I'm storing, here 24 bits of tag rather than all 32 bits of the address? Any ideas? Well, it would certainly work if I stored all 32, but it would be wasting space in my memory, which we know is very dear to us, okay? And so since I have information in my index about the address, I don't actually have to include it in the tag, and we'll explain that in a bit more detail in just a second. So in this example here, what I've got is, we said our offset is 0, my index is 3, and my tag is 0x40. So this means I'm going to look at the line with index of 3, and now I'm going to check what the tag is. Well, the tag is 0x40, which is the one I'm looking for, so I got a hit. Okay, and so what happens? I go ahead and I look at the data that's on that line, and I give that data back to my processor. Okay? Now suppose I looked for the address 0x4008. Well, in binary, this is exactly the same, except that down here, my index, instead of being a 3, is a 2. So is this address in my cache? No. right? Because the address that's at index 2 has a tag of 0x58, not 0x40. Okay, so if I was to look for this address, I would get a miss. And so then I would have to go and communicate with main memory in order to bring that piece of data into my cache. Okay, now suppose we wanted to try going backwards a little bit, and I said to you, can you tell me, based on the fact that these first 3 lines here have a tag of 0x58, what address in main memory those correspond to? Do we have enough information to do that? The answer is certainly yes, because otherwise we wouldn't be able to know whether we were getting the right thing from our cache or not. And so basically, if you look at the tag together with the index and the offset bits, you can recreate the address that this came from. And so if we look at the tag 0x58, we translated it here into binary, we're then going to put in the index 0, 1, or 2, depending on which line of the cache we're coming from. And finally, the last 2 bits are 0, 0 once again. And we're going to end up with 0x5800, 5804, and 5808. Those are the addresses that correspond to these 3 locations at the top of our cache. Okay? So the key to notice here is that we're saving memory by taking these index bits, which are identifying a portion of our address, and not including it as part of our tag. Okay, any questions about that? Good. Okay, so far we've looked at caches where we bring in 1 word at a time. Okay, and we've talked about storing 32 bits plus the tag plus the valid bit in each line of my cache. But that might not be the most efficient way to make use of our cache, because we learned last time about this concept of locality. And so what did locality tell us? It said that if I'm accessing, let's say, an instruction at some point in time, it's very likely that I'm going to access a nearby instruction at another point in time shortly thereafter. So if I'm going to pay the penalty of having to go to main memory and bring some data, why don't I just bring in a few more words together with it? That's not going to add too much to my overall time. And in the meantime, I was able to, let's say, bring 4 words instead of just 1. And hopefully, the next 3 requests will be hits. Okay? So the idea is that we might want this to be larger than 1. And there are a few advantages if you take a close look here. The first is that if you take a look at the ratio of how many bits you're using for data versus your tag, which is just identifying your address, you see that in the case where I had 1 word, I had 32 bits of data, and then I had 20, I think it was 24 or 20, maybe it was whatever. I got to look back at that. Oh, this was a different example. It was 27 bits of tag. And so you basically end up in a situation where your tag is almost close to half of the size of your memory. And in this example, where I have 4 words, then I have 128 bits of data for 26 bits of tag. And so now my ratio is much better. Okay, so the first thing is that I'm able to actually store more real data in the same size memory if I use this block a size that's greater than 1. The second thing is I benefit from locality, so hopefully I'll actually get a few additional hits and improve my hit rate. The potential disadvantage is that if the total size of my cache is fixed, then by making the number of blocks per line larger, it's going to mean that the total number of lines in my cache is going to go down. And so there is a possibility that I might not have enough lines in my cache for the different pieces of the data that I need to access, and as a result, that might actually increase my miss rate. Okay, so we have to take all of these things into consideration. And so how do I address a cache that looks like this? It's almost the same. Now the offset bits, instead of just assuming the bottom 2 are 0, 0, we're going to consider the 4 bottom bits to be our offset. So the bottom 2 are still going to be 0, 0 to get our word alignment. And then the next 2 are going to identify which one of these words in a particular line of cache is the one we're actually trying to access. Then we're going to have, in this case, we have just 4 lines, and so we have 2 bits of index to select one of these lines. And then the rest of the bits are our tag, which we're left with 26 bits, and so that means that our tag is going to be 26 bits wide in this situation. Okay, so we already talked a little bit about the trade-offs of having larger block sizes. Let's look a little bit more concretely at this. So we said that if we have, 1 block that I'm bringing in from memory versus, say, 4 blocks, well, I'm not going to pay 4 times as much in order to bring that data in from memory. Okay, I have this kind of, this overhead over here is the amount it takes me to bring that first word from memory. But then if I want to get consecutive ones after that, it adds a little bit more to the amount of time it takes, but not, it's not a multiplicative factor of the same as the first byte. So there is value in bringing in multiple bytes rather than paying this penalty every single time for every single word. What about my miss ratio? Well, we said that if we increase our block size, we go from 1 to, say, 4, we expect that we're going to be able to benefit from locality because we expect that the instructions that are nearby we're going to access, and so as a result, my miss rate is going to go up. However, if I continue increasing my block size forever, then the effect of that is that, not say forever, but obviously more than I need to, then what happens is that the number of lines in my cache becomes very small. Okay, and so as a result, I start to have what we call conflict misses because I don't have enough spaces in my cache to retain the different types of data. So remember, last time we looked at this working set in a particular time, delta t. We found that that working set was not so large, but you still have to have enough room in your cache to fit that working set in order to get the high performance. So basically what we do is we put these two together and we take a look at what our average memory access time is, and we find that essentially there's a point of diminishing returns, and things actually start to get worse after that. And this block size here turns out to be on most modern processors about 64 bytes or 16 words. Okay, and so that's typically what you'll see. It's certainly better to have multiple blocks than to have just one, but after a certain point, it doesn't help you. Okay, so let's look at a quick example of a direct mapped cache. Suppose that I have a 3-instruction program, and my instructions begin at address 1024. And then this 3-instruction program accesses data. The data is located at address 37, 38, and 39. Okay? Now, my direct map cache has 1024 lines. And just for the sake of simplifying this example, let's assume we're using word addressing instead of byte addressing. So we're not worrying about those bottom 2 bits. So if we look at where address 1024 is going to go, it's going to go into the index 0 in our cache. If we look at where 1025 is going to go, that's going to go into index 1. 1026 is going to go into index 2, and then we're going to repeat our loop, so we go back to 1024, which is back to index 0. For our data, we have 37, 38, and 39, which map to indices 37, 38, and 39. And so what we see here is that all of the data and all of the instructions of this loop are going to fit in our cache. And so we're going to get 100% hit rate in this particular example. Okay? But suppose I made just a very slight change, and now I'm running the exact same piece of code, except that this time my data, instead of starting at address 37, is starting at address 2048. So now what happens? Do I get the same hit rate? No, right? Because what happens now is my first instruction maps to, once again, line index 0, but this time my first piece of data maps to that same line as well. So what's going to happen is I bring the piece of code in, and then I need to bring the piece of data in that corresponds to that line of code, and it's going to take out that line of the instruction that I just brought in. Okay? The same thing is going to happen with the next two instructions and their corresponding pieces of data. And so then when I go to repeat the loop, even though I at one point brought my instruction in, when I go to access it, it's not going to be there. Same goes for the data. And so I'm going to have 100% miss rate in this example. Okay? So the problem with this is what we call conflict misses, is that in our direct mapped cache, there's exactly one line in our cache that a particular address goes to. And so if you happen to be in a situation where the multiple pieces of data that you need map to that same line in the cache, then you're going to have conflicts. So how can we fix that? Well, we can go to the other extreme, okay? And we can offer what's called fully associative caches. The way these caches work is you don't have an index that's telling you which line of your cache to go into. Instead, you can put your data in any line of the cache. But what this means is that now, instead of comparing the tag coming from my address to a single tag, I now have to compare to every single tag in my cache. Okay, so this becomes very expensive. The amount of comparator logic that I need here becomes huge in order to support a fully associative cache. Okay, but I certainly have the most flexibility in the sense that my data can go anywhere, and so I don't have any of these conflict type of misses. Okay, and so the way, once again, this would work is you would use your offset bits to identify which of the blocks you want, and then you would use your tag bits to compare to every single tag and identify which is the one, if any, that matches your tag, and if so, return that piece of data. Okay, so of course, that's not good enough for us either. And so what we end up with is we want a hybrid of the two, okay? And so we also have what's called n-way set associative cache. And so this is a combination of the two. You can kind of think of an n-way set associative cache as an n direct mapped caches. And so the way that this works is in an n-way set associative cache, you have a total of n places that any particular address can map to. So what's going on here is that your index is going to pick a line, which we call a set, okay? And in this set, you'll have 4 possible ways or 4 possible places that you could pick in order to put your piece of data, okay? So what does that mean in terms of my comparators? It means that it's certainly better than my fully associative cache, because now I only have to have a total of 4 comparators, not 1 for every single line in my cache. It also means that I don't have as many conflict misses as I did with my direct mapped cache, because now I have 4 possible places where things that have the same index can go in, okay? And so I can store them, all 4 of those at the same time in my cache. All right, so let's take a look at an example. Here we've got a 3-way 8-set cache. Okay, so the 8 sets refers to these 8 lines in our cache, which means our index is going to be how many bits? 3, right? So 3 bits picks one of these sets. Now, is it okay that in my example here, the ways is not a power of 2? It actually is, because this isn't actually making any use of a portion of my address. And so typically you don't see this. You will typically see like 2, 4, or 8, but there isn't anything that's actually keeping you from being able to support something that's not a power of 2 here. And so then what's going to happen is I pick my set. The data that corresponds to to each location in that set, together with a tag, are going to be brought down here. Now I'm going to do the comparison of the tag that's in my incoming address with each one of these. And then if I get a hit on one of them, it's going to drive what we call here it's an enabled buffer. And so if there's a hit, then it will allow the data to come out from here onto this bus over here, which is then going to feed the data back to my CPU. And so whichever one of my ways resulted in a hit will feed the data back. And if none of them resulted in a hit, then my multiplexer here is going to say, oh, you have to go get your data from memory. Okay? All right. So when we saw this, this graph last time when we talked about working set sizes. And you see here that if you look at a certain time delta t, then the working set size is limited, right? It only goes so high. And so how do we figure out, how big our cache needs to be in order to be able to satisfy the entire working set size? Well, if we first look at, let's say, our code, right? Here, every one of these dots represents a different instruction. But do we need to have a different way for every one of these instructions? I don't, because the way that I am indexing my cache will take care of this for me, right? So instructions that are near each other are by default going to go into different lines of my cache, okay? So if I have, here's an instruction, let's say my tag is A, the bottom is 0, and the index is 0, 0, then the next one is 0, 1, next one is 0, 2. These are actually instructions that are close to each other in memory. Let's actually do it in binary. Let's say these were my addresses, okay? So what's going to happen, though, is that when I map into my cache, this address is going to map to index 0. This next one is going to map to index 1, and this one after that is going to map to index 2, okay? Which means that my consecutive instructions are going to, by just the way that I'm searching in my cache, going to actually end up being in different lines of my cache. And so we're satisfying the spatial locality, which is the fact that we might be looking for instructions that are near each other, by simply making sure that the index bits are coming from this part of our address. What would happen, I could have chosen, right, to take my index bits from over here, let's say, right? What's the problem with that? The problem is that then I lose that spatial locality that I'm getting from picking my index bits on the low end of my address. Is that clear? Good. Okay, so we know that these instructions, the multiple instructions that are near each other, those can already be handled by the cache. So now what we have to figure out is, well, how many different groups like that do we have? And so we have, one piece for the code, another for the stack, one or maybe two for the data. And so, you find that you have maybe, let's say, 4-way associativity would solve your problem. And let's say if delta t was to grow, and you ended up spanning 2 of these or something like that, then maybe you'd have 8-way. And so what we find is that really the associativity that you actually need in order to get almost all the bang for your buck is not really that high. Basically, if we look at what happens as we increase associativity, our hit time goes up, okay? Because now we have more logic that's going to have to compare, which one of my ways matched, and as a result of that, that's going to directly affect the amount of time it takes me to determine if I got a hit or not. Similarly, we know that our average memory access time, as we increase the number of ways, initially it's going to get better because we're going to get rid of our conflict misses. But eventually, if I make my ways, the number of ways so large and the cache size is fixed, then I'm not going to have enough unique locations in my cache so that I can actually fit the entire working set size in the cache at one time. Okay, and so once again, there's a minimum here where we find that it ends up being the most efficient for us to use, and this typically falls around 4 or 8-way associativity. And in fact, if you look at this plot here on the left, which shows you miss ratios, you'll also see that once you get to some kind of a reasonable cache size, there's really essentially hardly any benefit to going from a 4 or 8 set associative cache to a fully associative cache, which is way, way, way more expensive. Okay? Okay, so we've learned about a lot of things so far. So we've got 3 different types of caches. We have direct mapped caches, where the way that they work is any given address can map to exactly one line. And so to determine if we have the right location, we simply need to do one tag comparison. We have our n-way set associative cache, where any address can map to n different locations. And so here we have to do n separate comparisons to see whether or not our address matches one of the tags. And finally, we have our fully associative cache, where any address can go in any line of the cache, and that means that we need the number of comparators equal to the number of lines in my cache. Okay, so there's one issue that we still haven't dealt with, which is, suppose, I've been running for a while and my cache is full, and now I get a miss, okay? Before I can bring that piece of data back into my cache, I have to figure out which piece of data do I take out of my cache, okay? And so we have this notion of what's called a replacement policy. Now, do I have this issue in a direct mapped cache? No, because in a direct mapped cache, it doesn't matter where I put the things. The address always corresponds to exactly one location. So there's no choice to be made, right? If I'm looking for address X, I'm going to find the index that address X is going to go into. Whatever happened to be in that index, let's say it was index cache line 2, will have to be taken out and sent back to main memory. In my set associative and fully associative caches, however, I do have a choice, right? If the address that I'm looking for, let's say, maps to set 4, let's say, then I can choose to retake this one out, or this one out, or this one out. And so how do I go about making that decision? Well, there's a few strategies one could use. So ideally, if I could somehow tell the future, the one that I want to take out is the one that's going to be used the most distant time in the future. But clearly we can't tell the future, so we need some kind of algorithm to try to emulate what it is that we're trying to achieve. And so what we want to do is we want to take a look at the addresses that we've seen so far and use them in order to kind of predict what we think is going to happen in the near future. And then we're going to replace the one that we think is the least likely to be used. And so what this leads us to is a replacement policy known as least recently used, okay? And so the way this works is you keep track of when you brought things into your cache and when they were most recently accessed, okay? So if I have, let's just say, that I brought in addresses, 2, 4, and 8 into my cache. And the way that I accessed them was first I accessed address 2, then address 8, then address 4, then I went back to address 2, and now all of a sudden, let's say I'm out of space in my cache. Well, it's not going to be the 2 that I want to get rid of because that's actually what I used most recently. So instead, it's the 8 that I'll take out of my cache, assuming that I have a fully associative cache and I can pick absolutely any location. And the goal is that I'm saying, well, this principle of temporal locality says that if I recently access the address 2, chances are that in the near future I'm going to want to access it again. Okay, and so I want to leave that one in my cache. I want to take out the one that I haven't used for the longest amount of time. Now, it turns out that actually implementing least recently used in hardware is expensive because you have n factorial possible orderings of all of the, we had to remember exactly the order of how, in which the addresses came in and when we accessed them. And so n factorial orderings leads you to log of n factorial in terms of the number of bits that you need, which then corresponds to n log n total number of bits to represent the number of states in order to actually keep that least recently used algorithm. And so it turns out that that's actually quite expensive. And so often what's done is an approximation to least recently used. So it's something that comes very close to it, but with potentially not quite as expensive hardware as this actual least recently used would require. And there are also a couple other policies that are used, although least recently used is definitely the most popular and the one you'll hear about the most. But just to mention a couple others, you could use first in, first out. So basically, whatever was brought in first, regardless of when it was accessed, would be taken out next. And so in this example, because we brought the 2 in first, I would ignore the fact that I accessed it again, and first in, first out, the 2 would be the one that I would get rid of next. Okay? Another choice is random. And well, you basically know how random works. And now, aside from random, regardless of which algorithm I pick, you can never be guaranteed that it's going to give you the best solution. So there's always going to be some kind of data access that's going to make that particular solution not behave well. And we'll take a look at a couple of examples of that in a moment. Okay, so one last piece to worry about. When we write things back into main memory, okay? So we have a choice of when we're going to do this. If we need to write something to our cache, I can do one of the following. My first choice is what's called write through. So if I write to my cache, I'm going to write to the updated value in my cache, and at the same time, I'm going to initiate a write to my main memory in order to keep my main memory in sync with what's in my cache, okay? And I can actually have my CPU halt and wait until I'm done with that write so that they stay consistent. Obviously, there are some drawbacks to that. While it's simple and easy to implement, the drawback is that it's slow and wastes a lot of bandwidth. So our next choice is what's called write behind. Okay, the way that this one works is, again, I write to my cache, and then I begin my write to my main memory, but I don't wait for it to complete. Okay, instead, I continue working and doing some other things, and so I have some parallelization. But, of course, if I need to now get something else from main memory because I got a miss, all of a sudden I am in a situation where I now have to halt and wait for the CPU to catch up. And so the one that works the best, which is really the only one that's used, is what's called write back. Okay, and the way that this one works is that you're only write to your cache. Okay? And only when you need to replace or take a piece of data out of your cache do you actually go and write it back to main memory. Why is that useful? Well, suppose that, I'm writing to some variable x, right? I might be making a lot of intermediate calculations, right? And I don't actually need to know all those intermediate values. The only one that I actually need to store is the final result. And so in the meantime, I wasted all this bandwidth writing every single intermediate value back to memory. No real need to do that. So instead, the way that write back works is it says only when I'm done using this because I have to take it out of my cache, now I know that I'm really done and it's time to write that back to memory. Okay, so in a little bit more detail, what does that look like? Well, this was the algorithm we saw at the beginning of lecture, which told us, how do we do both reads and writes in the case of a hit or a miss, okay? So what's going to change is that before we said that on a write, in addition to writing your data to your cache, you would also initiate a write to your main memory. Now we're saying we're not going to do that, okay? Instead, what we're going to do is only when it's time to have the replacement, because you have to take a line out of your cache, at that point, you're going to write your data back to main memory and to the address that it corresponds to. Okay, so can we go even a little bit better than this? And it turns out that we can by adding this notion of dirty bits. So what is a dirty bit? Anyone care to take a guess? All right, well, a dirty bit basically just means that you actually wrote something to that location in the cache, okay? So how does this work? If I do a read, even if I had a miss, that's not making my location be considered dirty, because on a miss, what happens? I went to main memory, I brought my data into my cache, but now my main memory and my cache are still consistent. Okay, so for that kind of situation, I set my dirty bit to 0. But what if I do a write? Okay, because we're now doing the write back policy, my cache and my main memory are now going to be inconsistent. And so anytime I do a write, whether it's a hit or a miss, I'm going to set this dirty bit to 1. And then when it's time to take a particular line out of the cache because I need to replace it in order to bring something else, at that point in time, I check this dirty bit. If it's 1, then I'm going to write it back to memory. But if it's 0, that means that I never changed its value, which means that there's no need for me to write it back because main memory has the same value. Okay? All right. So, to summarize, we have a lot of trade-offs to consider, right? And how do we go about making our decisions about, which parameters to actually pick? It's the same thing we've been talking about for all of the other things that we're learning, which is we run benchmarks. We run benchmarks that play with the different parameters. And so we play with the cache size, where there's a trade-off between lower miss rate and higher hit time. We change the block size. Again, we know that going more than 1 is useful because it gives you some spatial locality, but at some point it starts to give diminishing returns. We take a look at our associativity. Again, we find that somewhere between 4 and 8-way associative is typically where we want to be. And we consider different replacement algorithms. Generally, as I mentioned, something like least recently used is what's used. And finally, we have our write policy, which determines when it is that we actually have to write things back to memory. And so if you analyze this using benchmarks, you'll determine for your needs, how do you want to set up these parameters for your cache. So what I'd like to do with the few minutes that we have remaining is take a look at a few accesses. What we're going to look at is if I want to access a particular sequence of addresses in these different types of caches, how does the performance compare? Okay? And the example that we're going to work with, just to make it easy, is going to be a cache that has 8 words in it. Okay, so the direct mapped has 8 words, the two-way has 4 sets, each of 2 words, and the fully associative has 8 independent locations, which means you can map to any of them. All right, now suppose that I'm telling you that the sequence of addresses that I want to access are 0, 16, then 4, and then 36, and then I'm going to repeat it in a big loop, okay? So I want to figure out how do my hit rates compare for the different types of caches. Well, for the address 0, the index is going to be is 0 for my direct map cache. It's also going to be 0 for my two-way set associative cache, so it'll go in one of these 2 locations. And for the fully associative cache, it can go anywhere. So let's just fill in the top box. Now I go look at address 16, okay? Recall that the bottom 2 bits are just doing my word alignment. So the next 3 bits are going to give me my index for my direct mapped cache. So the index for address 16, which is this in binary, is 100. So that means that address 16, and remember, what's actually going to go in your cache eventually is going to be the address as well as your data. But for this example, I'm just showing the addresses and where that corresponding data is going to get stored. So it's going to go into this index 4 in your cache. Now, and the two-way associative cache, the index is actually just 2 bits, not 3. And so here, your index is actually 0. I actually did that wrong. That should be 1 lower, so sorry about that. But in any case, your index for the 16 is 0, but in the two-way set associative cache, even though these map to the same set, I have 2 different choices. And so I'm going to be able to have both the 0 and the 16 in my cache at the same time. All right, what about my fully associative? Again, no problem. I can just use another new location for that. Now, the next location that I want to look at is address 4. Okay, address 4 has an index of 1 for both my direct mapped and my two-way set associative, and in my fully associative, no problem. And finally, address 36. Well, what happens for address 36? Address 36 has an index of 1 for both the direct mapped and the two-way set associative. So what does this mean? It means that in my direct map, I'm going to have a conflict because both the 4 and the 36 map to the same location in my cache. In my two-way set associative, though, I don't have this conflict because I have 2 possible locations that they can go to. And in my fully associative, I also don't have any problems because I can put it anywhere. So as a result, what do we have as far as hit rates are concerned? In our direct mapped cache, we have a 50% hit rate for this particular example. And in our two-way and fully associative caches, we have a 100% hit rate. Okay? Now, suppose, though, that we change our, the way in which we access our data a little bit. And here we've got this sequence of addresses. Okay? So we've got 0, 4, 8, 12, 16, and so on to 32, and then it repeats. Okay, now you'll notice that there are actually 9 distinct addresses here. So let's see what happens in this case. In our direct mapped cache, what happens is we start off with a 0, it goes into index 0, then 4, 8, so on until 28. Then when we get back to 32, 32 is going to map to the same line as the 0. And so here we're going to get a miss for the 0 and the 32, but everything else is going to be a hit. Okay, so our hit ratio is 7 out of 9. Okay, what about our two-way set associative cache? In our two-way set associative cache, we now just have 4 sets, right? We added some flexibility because for any particular index, it can go in one of 2 locations. But for this particular example, what ends up happening is that, let's say you would put your 0 here, and you're using, let's say, a least recently used algorithm for replacement. So when you get to the 16, it comes into this second way of your index 0. But then you get to 32, and that also needs to go to index 0. And so let's say your 32 replaces this 0. And now you need to go and access 0 again. Well, you just got rid of it, and so now you need to put the 0 in place of the 16, and so on and so forth. And so what ends up happening is that for your accesses of 0, 16, and 32, you always are going to get a miss in this particular configuration. And so here, our hit rate is 6 out of 9. Now let's take a look at what happens in our fully associative cache. This is kind of the worst case scenario, because while we have the most flexibility and that our addresses can go into any one of these locations, if we're using a least recently used algorithm for replacement, what's going to happen is we're going to start filling in from 0 to 28. We now get to 32. Well, 0 is my least recently used location, so I'm going to replace it right before I need to access it again. Okay, so now I want to access 0 again. That's going to replace my 4 again right before I want to access it again. And so what's going to end up happening is that every single one of my requests is going to result in a miss, okay? And so here, my hit rate is 0%. So it's definitely possible that even though you're giving yourself more flexibility by adding associativity, you could still have a scenario where your hit rate is actually worse for a fully associative cache than it is for a direct mapped or a two-way set associative. Okay, one last example is this is very similar except that the addresses jump here a little bit. And so what happens here is that our direct map cache now does much more poorly because addresses 32 through 44 map to the same locations as 0 through 12. And so now we've reduced our hit rate to 1 out of 9. And then for our two-way and fully associative caches, things actually look basically the same. In the two-way, the locations 0, 16, and 32 are conflicting with each other, so we have 6 out of 9. In the fully associative, because we're still dealing with 9 different unique numbers, the result is going to be 100% miss rate. Okay? All right, that's it for today. We'll see you next week. Have a nice weekend, everybody.